Okay, so since it's been a while since our last class, I believe, I will just do a quick review of some very important things that we were talking about in the last class, and which I have just, for which I've just returned some of your in-class problem things. So take a look at this slide. Some of you had slight notational issues, so if you see a correction to what you wrote, remember that covariance has to be between two things. So it doesn't make sense to say things like cov x. You must say cov x with what? You can have covariance with yourself, which is your variance, but don't write just cov x. That doesn't mean anything. It's cov x comma something. You have to covariate it with something else. This is a very useful thing to remember. The covariance of this with this, you can break it up using associate law. So AC comes out, then you have cov x comma u, and you dealt with a very irritating problem, which you did really well, and got 8.8, I think. That one. And, okay, now remember that expected values are easier things to deal with. You can have x and y, two different random variables, and function all. If you want to split up an expected value, you can. You don't need independence. However, to split up a product, the expected value of a product, for this to be true, you need x and y to be independent. So these are the small, subtle things you need to be aware of. The simplest case is you can only say exy is ex times ey if you know x and y are independent. Otherwise, you cannot. Okay? Variance is more fussy. You can split up a variance like this if you know x and y are independent. See, variance is a harder thing to please. Expected values are less demanding. Variance, even to split up this, requires independence, even a plus. Don't even start talking about products. That's not even true at all. Okay. Okay. In general, you can break up a variance if you want to remember this rather useful formula. If you don't want to remember this, you can always resort to writing this as cov ax plus by ax plus by. You can get this same result by using this. But this is not too difficult to remember. A squared, b squared, 2ab. And then, of course, for any constant, the variance of a constant is zero. Constants don't vary. And the covariance of a random variable with any constant is zero because the constant doesn't change. So there's no covariance at all. Okay. So with all these things there, we then told you something about correlation. The definition of correlation is the covariance over the square root of the variance of x times the variance of y. You will find that in some earlier definition somewhere. And if you have x and y independent, then they are not correlated. But the other way is not necessarily true. You can dream up two random variables that have zero correlation, but are not independent. All right, so you can't necessarily say that. Okay, so let's do, I think we did not finish. Let me see, I wrote in my notes after class that we didn't finish example 103, I think. Let me just have a look. Why did I say we didn't finish it? Oh no, I think okay, yeah, I think this is very good for us to revise. I think we have talked about this. I'll start today by revising this example. So we said X represents benefit paid to the surgeon. Y is the benefit, the part paid to the hospital. So X is the surgeon fee, Y is the hospital fee. Now the variance of X is 5,000, the variance of Y is 10,000, the variance of the total benefit is 17K. Notice we never told you X and Y are independent. So don't assume that. So now, due to increasing medical costs, X increases by 100 flat, and Y goes up by 10%. So that's reflected in this statement. The new total benefit now, due to inflation, if you like, is X plus 100 plus 1.1 Y. The X gets increased by a flat rate of 100, and Y gets scaled by 10% more. Okay? So I want you now to calculate the variance of the total benefit. So the variance of the total benefit is obviously this variance. How do you break this up? Well, follow all the rules I gave you. Basically, adding constants doesn't change the variability at all. So you can just ignore this. And we've just revised this formula. How do you open up var x plus 1.1y? Well, you have var x. Then you have your 1.1 now squares and comes out. So you have this. And then you have twice the covariance of this with the and the this with this first, and then the 1.1 comes out as well. So you can do this at any level of speed that you're comfortable with. Basically, constants come out and are squared, but if it's a covariance, you just take that out directly and do square. Too easy. Okay, so the only challenge that remains is we are given var x and var y, but we are not given cov xy. So you have to figure that out. How do you get cov xy? Well, you know that var x plus y is 17k according to the problem. You also know that var x plus y in general is expanded this way. We just ran over that formula. So a little bit of simple algebra just tells you, oh, the covariance is 1000. And dump it all in and you get the final answer. So this is not a trivial problem. It requires knowledge of how variances and covariances behave together. Yeah, I think we didn't finish this last part. I think we ran out of time. So that's why I noted down that we didn't finish it. Is this okay? Is this example okay? I know there's a lot of numbers, but the ideas are quite basic. So the key thing is don't assume var x plus y is var x plus var y. That's the moral of the story. That's not necessarily always true. And you'll be surprised how many professors even who didn't have much probability background, they think var x plus y is always var x plus var y. And that leads to problems. If the covariance is small, fine. The problem is not so critical. But if the covariance is high, you end up with highly inaccurate answers. And yes, the covariance sitting around it's an unnecessary it's a necessary evil. It's a necessary complication, unfortunately. It makes our computation less smooth, and you have to think about, do these covary or not? It can become a real pain in the neck. All right, it's quite difficult to always have to remember that you have to account for covariance, but that's how it is. Okay, so before we continue with this, let's go back to our slides. I'm going to introduce, well, we've learned conditional probability, but not in the context of random variables. So I'll introduce it now. You know that if I give you an event A and event B, the probability of A given B is the probability of A and B over PB. We know that. We just done the exam. So this concept is the same thing translated to random variable. If I ask you to construct the conditional probability mass function, is it the word conditional now? You know what probability mass functions are. Probability mass functions are statements about, well, tell me what's the probability of something, like that. Now this is a conditional PMF. Conditional why? Because I'm conditioning on something. So if I have two random variables x and y, it is defined that the probability that x is x, given y is something. I put a star here to mean this is some specific value that I choose. It follows the same definition that what you use. So it's nothing new. You take the intersection of both and you divide by the right side. So you need to know conditional probability first. Okay? Okay. Now, here's the part that students tend to get confused about. Now, we'll do many examples, so don't worry. I'll even ask you in ICP to construct examples to show me that you understand what this is. What is a conditional expectation? Actually, it's not a big deal. Somehow, this is something that tends to be a big deal for students because it is a little bit harder to understand, but it's actually mechanically, it functions like an expected value. The conditional expected value, I don't know whether to give the game away. You've probably seen all the buttons. Right? The button for this class is px given y. And you will see next time. Okay, so what is E x given y? Well, it just means, don't you know how to find EX? Okay, I'm going to cover some things up. Isn't EX found this way? You take all the X values that you have, scale it by the probability and sum. Now, because you want a conditional expected value, you don't use the probabilities per se, you use the conditional probabilities and you proceed to normal. Did you see that? I'll cover this up again. If I cover this up and I cover this up, don't I get EX? Now I put this back, you just add a slash. It's basically the conditional expected values are what's the expected value of the conditional PMF? What's conditional variance? Well, once again, let's block this out. Block this out. Block this out. And I don't have enough hands, okay? But if I block that out, don't I get the variance of X again? See? So conditional variance is nothing more than using the conditional probabilities to compute the expected values that you use. That's it. So that's the definition of conditional variance, okay? So with those definitions in, now the rest of the time will be devoted to doing a bunch of questions. So let's deal with some examples. So here's a joint probability function. You should be quite comfortable with this. Just you need X and Y change together in this way. Find this. Okay. So can anyone just just yell out? Right? This is a fraction. Okay. It's something divided by something. Can you tell me what or what do you need to do? You want to find the basically you want to know how does X behave conditional on me knowing that Y is 2. What would you need to do? I would need to compile a list of joint probabilities and between various values of X and Y is equal to how much? 2. And before all that, what's the key probability that I need to compute? What sits in the denominator all the cases? The fact that you want to find this for different values of X means that the key probability you have to start with is to find the probability that Y is 2. Good. So can you do that? What is the probability that Y is 2? That's a very, very easy question. The probability that Y is 2 is what? Oh, my brain has left for the day. Did you get 0.5? Right, you just sum up. So, okay, so see what I did here? And you see how brief these things can be expressed. So I'm just going to show you some notation. Let me expand this a little bit. Yes. Okay. See? X slash Y. This is X1. Condition on the fact that Y is 2. That's what it means. See? This is joint. 1 and 2 over Y2 alone. And that's why the subscripts are important. This is conditional. This is joint. And this is marginal. They're all different. Marginal Y, joint XY, there's a comma, conditional X slash Y. All right. And what will it, okay, so how many X's must we do? 1, 2, 3, and 4. I mean, 2 is easy because we know it's going to be 0, but you need to do 1, 2, 3, and 4. Okay, so the rest will look like this. Okay. Why is a conditional probability distribution a probability distribution in its own right? Because it also sums to 1. To me, that's quite bizarre. I don't know whether you realize. And when you see continuous ones next time, it's even more bizarre because you can condition on infinitely many and you keep generating distributions that do sum to 1. It seems sometimes I have a hard time reconciling. We know that the whole table sums to 1. We know that. For a joint probability distribution to be valid, it has to sum to 1. That's good. But now you are forming from a joint distribution a conditional, and all the conditional distributions must also sum to 1. To me, that's very, sometimes a little bit, it causes me a little bit of, it makes me feel a bit weird. No, it doesn't make me feel good. It seems kind of fake, Do you know what I'm saying? Is that we know the original joint sums to one, but by taking a ratio like this, you kind of like generate another family of conditional distributions which, in their own right, also all sum to one. And it's true whether you condition on y is equal to two, or you condition on y is equal to one, or you condition on y is equal to three, or you do it the other way. You can also say what's the probability distribution of y condition on x. You can also do that. You can generate a whole scheme of probability distributions that are conditional, and they all will sum to one, which to me really freaks me out. And it's even worse when you see a continuous, jointly continuous x and y, like a, you all know the bell curve? There's a three-dimensional bell curve, like a, imagine a blanket and there's someone under it, like that. So you can slice it in infinitely many slices. Every slice is going to generate a density function that also integrates to one. So it's very, to me, it's weird. Very, very weird, but that's how it is. Okay? So it's basically scaling what the probabilities are in a smaller world. Because you know y is equal to has happened, you're only looking at the world where y is 2. So it's like people say you have such a narrow worldview. Conditional probabilities are like that. It's a very narrow worldview. In my world, y is 2 already. And that's why you scale all the probabilities. Like you're shrinking your world to a world where the probability is only 0.5, something like that. So it's quite bizarre, but that gives you an intuition of what conditional probability actually even is. Okay. Okay, let's see another one. Okay, so if you want to state okay, yeah, let's look at another one. Okay, the joint probability function of x and y is summarized by this table. Okay, tell you what, why don't you do this as an ICT with your friends? Okay, generate this for all possible x's, then try to compute this and see if you can come up with the right answer. You know what this means, right? This is the expected value of the newly generated distribution. Don't worry if you don't know how to write the notation properly. That can be a pain, but show me the numbers that you would do, all right, that you would use. Are you all getting a nice answer for the exam? Is it 4?
I got.
Can anyone tell me why? And this one will make me very happy. Can anyone tell me intuitively why you know, without doing a single calculation, why it has to be 4? Yes. Good. Okay, see, I had a professor in grad school who was scary this way. His level of intuition was so good that he would be able to tell the answer with 2 Okay, I'm not like that, but when I looked at it, I was like, actually, there's no need to do anything. Why? So you know you're conditioning on 4, but I wanted you to do it a long way to practice, okay? But you didn't have to. I I know why it's 4 already. So this whole world goes away. See? And in this world, x can only take the value 3.5 because there's zero property, as Maggie said. See? And then these are symmetric. See? This is its own private symmetric distribution, symmetric at 4. So you should get the expected value of x given y is equal to 4 to be 4. All right? But if you can't see that, that's okay. Don't freak out. You can do it the mechanical way. Get probability of y equals 4 first. And then just scale the rest. 3 given 4, 0.1 over 0.35. 4 given 4, 0.15 over 0.35. 5 given 4, 0.1 over 0.35. And I think at this stage, how would you, if you still can't see the symmetry, that's fine. How do you get the expected value of a conditional? What can x be? Well, it can be 0 and 0, but we don't waste our time with that. 3 times this plus 4 times this plus 5 times that, which does give you 4. All right. Good. So I'm glad you all can detect the symmetry. Now, suppose, okay. Okay, this problem, I think there's no symmetry. So, yeah, they really, I don't think so. So this is just, I don't think we'll spend time on this one. So I'll just show you the work, okay? This is just more practice to think about this. So find the joint probability distribution x and y. This is just basically a lot of quite tedious calculation, basically. Just filling it in according to the prescription. That's what you have. Okay, so here's your table. How do you find the things that you want to find? So you know by definition the expected value of y given x would be, well, all the y's that y could be times the conditional probability that follows the structure of what you want. That's basically what you need to do. So you will need to find a bunch of conditional probabilities like this. And we'll see. So if you want to write it out in all its glory, you have, you know that conditional probability is defined as joint over marginal. And this one, you can't rely on any symmetry to help you. It's just brute force. There's nothing else. All right, so the concept of conditional expectation is very, very important because conditioning things helps you get out of a jam in surprisingly many ways. One of my colleagues actually asked me a question about 2 weeks ago, and uh, and it was something that was causing us a little bit of consternation. And so to prove it, I used this old friend conditioning. So, but that's a little bit beyond the class. But just bear in mind that conditioning is something that's surprisingly useful. And if any of you ever goes on to grad school, you will, and if you do anything statistically related, you'll find that what I said is true. Conditioning is a very important concept to understand. Okay, I think we. Oh, okay, I want to talk about 107. Okay, this is your first chance to calculate conditional variance. You've not done that yet. Okay, so let's look at this one. A diagnostic test for the presence of a disease has two possible outcomes. One is for disease present and zero for disease not present. So X is the state of the patient in reality, and Y is what the diagnostic test says. Do you understand? So X is reality, Y is what the test says. So this kind of test is pretty okay. If you really don't have the disease and the test says you don't have the disease, that's about 80% of it. Uh, but of course, not every test is perfect. Sometimes you are having the disease, but the test says no, you don't. That's what it means, okay? And I think the rest you can understand. So that's the distribution of X and Y. So a good diagnostic test should spend most of its time here and also here. These two should be higher and these should be as low as possible because these are all wrong, basically, okay? Calculate var y given x is equal to 1. Can you do that, all right? How would you do that? Because we have not done conditional variance yet, but it's no big deal. You know to find conditional expectation. Conditional variance is you need to find y squared given x is equal to. This is a small enough problem that it's not super tedious to do. So give it a try, okay? What's the practical implication of this number? It's among those who have the disease, what's the variability of the kind of response you get from the test? That's what the practical implication is. How variable is your test in terms of its correctness for people who have the disease? Are we okay with this one? Okay, what are you all getting? Are you all seeing this? So first of all, you need to find obviously the probability that x is 1. Okay, find a marginal for x for 1. Then just find the conditional for y. You need that y because you're going to find all the ey and ey squared and all that. So you should have this quite simple thing. Then just evaluate these two things. What is the conditional expectation of y when you know x is 1? And what's the conditional expectation of y squared when you know x is 1? So uh, you just proceed this way. Immediately you can tell that the expected value of y when x is 1 must be just 1 times this, because the other option is y is 0, so you don't even have to bother. And then ey squared is even even easier because essentially it's the same. And then okay, the only thing I want to show is this formula. So the variance of y given x is 1 is ey squared given 1 minus the square of ey given 1. This is exactly how you find any variance. The only twist is now it's all conditional, conditional, conditional. Anyway, that's the answer. Now we're going to skip 108 because that's a, I don't think this class needs to go through that problem. So we won't do that. But we will look at 107A though, okay? I do want to look at 107A because that will give you a little bit. You may think, why am I stressing so much about this? Is because it looks quite easy to do, and it actually is, but you'll be surprised how quickly you will actually forget what this even means once you finish this class. So at least do this one, right? 107A, the discrete random variables x and y have this probability mass function. There are no symmetries here, so there's no shortcut, unfortunately. But there are not many numbers to play with. Can you find ex given y is equal to 1 and ex squared given y is equal to 1? So what are and let's not do this as an ICP, just do it on your own, right? That's just to prove to yourself that you know what these things mean. Okay? Anyone have any answers yet? Okay, so Ex given y is equal to 1 should be what? Condition on y is equal to 1. You should be seeing something like this. Let me see. Yeah, we obviously find this first. And so the expected value would be the conditional probability scaling like that. And you find it for 2. And so you find that expected value of x given y is equal to 1 should be just this. And you don't have to do it as you don't have to do it in as many steps as I have. But and maybe some of you were able to do it in your head as well. So you should get 1.6, which I hope makes sense. Because x is either 0 or 2, and the probability that it's 0 is lower than the probability that it's 2. So it spends more time near 2, in other words. So 1.6 is the answer, it should be intuitive point. There's more weight closer to see the probability here, the conditional probability. Good. So you have an intuitive feel for what's going on. So I'll save you some time. It's very tedious to do this for every single value of y. So I have reduced the work to just show the answer. If you did this one by one, I asked you to do it for when y is 1, and you did get this answer. You can do it for 2, you will get this. You can do it for 3. What am I getting at? What I'm trying to introduce here is the concept of conditional expectation that turns out to be a function of the thing you condition on. So far, you have been working with specific values of the conditioned variable. But I'm trying to show the class that actually any conditional expectation is actually a function of the thing you condition on. In other words, if I condition on different values of the variable y, I get a different conditional expectation. It's a function of the thing that you condition on, the value it takes. And so this is something that might blow your mind. Therefore, if we know y is random, because y is random, the value of this depends on the value of y, which means Ex given capital Y, if I find this function, can you foresee what I mean when I say Ex given Y is itself a random variable? Let me say this carefully again. When I give you a specific value of y, little y, you know how to find the expected value of x given y can be any of these things. And you get numbers. But do you see, therefore, that what this is depends on what you told me little y is. And this makes Ex given y a random variable because it can take different values depending on what y is. So there is something I want to introduce to the class. Writing this is not the same as writing this. This means tell me specifically what the expected value of x is, given that this random variable is at this specific numerical value. But once you have found this, expressing this in this way turns this thing into a random variable. Now, I'm not going to dwell too much about this in this class. But if you go on to do the probability exam, this is a concept that is very important. This is itself a random variable because its values change depending on what one is. That's what a random variable even is. Okay? But it's not something I'm going to dwell on in this class. In this class, you just need to understand how to do this and to realize that the conditional expectation can be a function of the thing that you condition on. In other words, it can have different answers depending on the value of y. So of course, you can go on to calculate ex squared given y is y. And of course, you can therefore find variance as well. So you will also find the conditional variance changes depending on your choice of what the other variable is, which makes the conditional variance itself also a random variable. Okay? But that's something I don't really want to dwell on. I'm just pointing it out in case you ever encounter this in grad school or some other place. So, right? That's just so you know. Okay. Are we okay with this one? The numerical one is okay. The random one takes a bit of thinking, but I'm not going to stress on that in this class, so don't worry. Yeah, I'm just putting it out there because you might hear this in a future class. The same, right? Okay, let's move on to chapter 7. I think we are done with this chapter. So there will be a homework opening today, all right? And it will be on these things. Okay, let's let's look at chapter 7. Okay. Now we'll have, I think, something that's a bit more fun. We're going to introduce you to the world of named probability distributions. These are famous distributions that are used to model many things. And because they're so famous, we are they're named, all right? So that people can use them again and again. The first one we're going to introduce is the binomial. Okay. Before we can talk about the binomial, we need to explain what a Bernoulli trial is. So a Bernoulli trial is anything you do that it can only have two outcomes, yes or no. Binary outcomes succeed or fail, yes or no. We typically label the probability of success with little p and failure to be q. You might think, why don't you just say 1 minus p? Yeah, you can. But when you derive stuff, sometimes you write 1 minus p so many times. So that's why people introduce q, but it's not important. So if you let x represent, you try a Bernoulli trial, you do Bernoulli trials n times. You perform n trials, each one with the same probability of succeeding each time. And then you measure among those n, how many of them did I succeed? That kind of random variable is called a binomial. All right, I'll say this again. A Bernoulli trial is one time you try something and you either succeed or you fail. It's binary. But you can do this a bunch of times. If you do n Bernoulli trials, each time with the same probability of succeeding, and another important assumption, all your trials are independent of each other, which means there's no learning taking place. You're not improving as you try. Every time you try, it's as if you've forgotten the previous experience already. So it's independent. If you collect the number of successes that you have in n tries, that creates the famous binomial random variable. It's called binomial because only a success or failure can happen. So the binomial, it has two parameters of importance. Obviously, you need to tell me how many times you tried something. And you need to tell me the individual probability of success on any try. Okay? And by the way, specifically if n is 1, some people call this the Bernoulli, but it's not very important. A binomial 1p is specifically called a Bernoulli to respect against the Bernoulli trial. Okay? So, here are some rules. Generally, if x is binomial np, then the probability that x is equal to x is ncx px1 minus pmn. Okay, let me explain that. Is it clear to you why this function governs binomial distribution? Well, I'll go through what. What does capital X measure? Uppercase X measures the number of successes you have when you try something n times. If you try something n times, how many times can you succeed? Actually, do you agree that when you do something n times, you might succeed never, or one time, or all the n times. I think that's pretty logical. You try something n times, maybe you succeed every time, or maybe you never succeed at all, or anything in between. This is very important. As we deal with more and more of these named distributions, this where it is valid thing becomes very important because it helps you distinguish what probability model we're in. So this has a name, you know. This is called the support of the distribution. You can add that to your slide. The range of values for which a rule applies is called the support of the distribution. What supports it? So this is the support of the binomial. Now I'll go to why this formula should make sense to you. If you do something n times, what's the probability that I succeeded x of those times? See, where x can be anything between 0 to n. I want to succeed x times. Don't you agree that this probability is p to the x, first of all? Yes. What are you assuming? When you say it's p to the x, do you know you're assuming independence? You are. And I want to fail how many times? If I succeed x times and I do n trials, I know that I must have failed n minus x times. So you multiply this together. But why? Can anyone explain to me why the need for the NCX in front? Yes. If you look at this specifically, what are you saying actually? You're saying that my first X trials were all successes, and my last n minus X trials were all failures. There is one way that could happen, but it's not the only way. And so you need to put that coefficient there, the NCX. And if you did your corrections for the exam, you'll find that many of you did not consider the number of ways something can happen. And that's NCX. Okay, so that explains it. Now, there are some wonderful proofs, and I hope to have the time to show you actually why this does sum to 1. Okay, but we'll get there. Is it intuitive to you that the expected value of x is n times p? I always tell people, well, always think of a very easy example to think about. Let's say your free throw rate is 1-4. Right? In the long run, you try 4 times, you win once. Right? You get it through the basket, 1 in 4. If I did 20 shots, how many would I expect to go into the basket? Is it an easy question? My free throw rate is a quarter. Okay? I do 20. How many do I expect to get in? 5. How do you get that? 20 times 1-4. So the NP formula is one of the most intuitive ones, and it is true. Of course, you don't prove it that way, but it is true that it is NP. And we will try to show it together as a class. But it's not required for the exam, but it's good for your math. So we will show you why it is NP. The variance is NP1 minus P. I have thought about this. I have no appealing intuition why this is true. Maybe you have some. This, to me, the NP formula is very intuitive. But NP1 minus P for the variance, I don't get somehow. So if you can dream up some easy, intuitive argument, let me know. Share with me. I learn it as a rule. I don't see the intuition why that should be the case. Okay? Please ignore this. We are no longer talking about moment generally, so we'll cross it out. Okay. It is important to remember the assumptions which are in place for a binomial random variable. We always assume that all the n trials are independent, which is not a valid assumption all the time, you know. With all the talk about AI and learning and all that, this is no longer true. AI is one of the most easy examples I can think of where it is not independent. As you feed more data into some kind of a bot that learns from older data, it is certainly not independent. As you give it more data, it learns. So the binomial model doesn't apply to artificial intelligence actually, because you learn more as you try something more, and you feed it more data, it knows more, or it gathers more information. So it is not true. So this kind of probability model depends on the assumption of independence. So you don't get smarter, in other words. Or you, as your free throws, you keep doing it, your success rate stays the same. It doesn't change. And not only are they independent, the probability of success stays constant. And I'm going to make a comment here. Many people cannot differentiate between questions that involve a p probability that doesn't change and one that does. I'll give you an illustration. If I talk about sampling people from the entire world, and let's talk about left-handed people, roughly 10% of the world is left-handed. So I could ask you a question like, if I sampled 30 people from all over the world, random, what's the probability of there being 5 left-handers out of the 30? What would you say? Well, you're trying something 30 times, and I want to know, out of the 30, I want 25 right-handers and 5 left-handers. Now, you need a probability of success. So let's say the probability of success of picking someone who's left-hand dominant is 10%. But do you know when you use a binomial model, what are you assuming? You're assuming that the 10% probability doesn't change once I've selected someone, because the population of the world is so big that taking out one left-handed person leaves behind a pool of another 8 billion people. So the effect of the change, the slight change in the probability of you being left-handed is so marginal, we ignore it. That is why the binomial model has this very key assumption. The probability of success stays constant through all the time. But this is not true in a problem like this one, which I'm going to describe. In this room, for example, there's only, I don't know, 12, yeah, 12, there are 12 people in the room. If I say, I want to know what's the probability of me selecting two people that are, I don't know, in some kind of Greek life or whatever that is. Okay, so some of you may be Greek life, some of you won't. But I cannot assume that once I've selected someone who is in Greek life, that probability stays the same, because this class is certainly finite in size. So when you have that kind of problem, actually that is another distribution which we'll be talking about in the next few weeks for the hypertrophy, where you have a finite pool of things to draw from. Your probability of success changes once you have picked someone out. You cannot assume it stays the same. This assumption assumes that you are actually sampling from an infinite pool of people, so that when you pull someone out, it does not affect the probability of success for them. So these are quite important distinctions which I want to get across to the class. So the binomial distribution assumes infinite populations from which you are drawing your trials. Okay, let's look at some examples. Okay, I think it's example 109. Okay. And I want you to just, on your own, if you like, write down the formulas for the probabilities. Don't evaluate anything. 40% of voters in a city are in favor of a ban of smoking. You can see how old this question is. Okay? These are not even a thing anymore. Okay? But believe me, when these things were proposed, they were considered highly controversial, because you say, aren't you infringing on the rights of smokers and all that? Okay. So 40% of voters are in favor of a certain ban. Okay? Suppose that 5 voters are randomly sampled. You see? Do you realize what are you saying? You are saying that the population of the city is so big that selecting people doesn't affect this probability. You are tacitly assuming that the city is infinite people. Drawing 5 people out, 1 person at a time, doesn't affect the probability overall of people supporting the ban. So can you write down, if I take out 5 people, what is the probability that in those 5, exactly 2 favor the ban? Is it obvious what the answer should be? The first thing that should come across your mind is 5C2 multiplied by what? 0.4 raised to the, so 5C2 and then 0.4 to the power of, is it clear? If it's not, I'll show you the main formula again. How many do you want in your sample of 5 to favor the band? 2. Probability of favoring the band is 0.4, so 0.4 squared. And then 0.8 raised to the 3, the other 3 people. All right? Something like that. That's it. As I said, you don't have to evaluate anything. All this you can do on your own time. I think for homework problems, I do ask that you find numerical answers. But on exams, this is perfectly fine. All right? Then things like less than 4 and all that, that's where things get very tedious. That, of course, you can use R to get binomial probabilities, and you are welcome to do that on your, if you want to, for your homework. On the exam, I would never ask you to evaluate these things. What's wrong with you? Why would I want you to do that? Okay? But you can be expected to write out the numbers that you. But if you want to get a number for it, I will let you use Google to check how R can give you these things in a flash. It's quite easy. Put in the parameters, the N, the P, and how many you want. But it's not important. Okay? For homework purposes, you might need to calculate what this is. For example, yes.
For part B, could you also do 1 minus?
Yes. Thank you, Freddie. That's a very good point. You can. You certainly can. And actually, you should always pick the direction that favors you. That's easier to do. Yes. Yes. That's the next thing I was going to say. This, what's the opposite event? It's the opposite is x greater equal to 4, right? So you can say this is 1 minus the probability of x greater equal to 4, which means you have only 2 cases to consider 4 and 5. Yes, certainly. Both ways will work. See, at least one favors the band means one. So it's very important, as I always tell my intro stat students, what's your success here? What's the success here? Success is favoring band. So if you want one or more favoring the band, well, the opposite event, to prove the point I just made, is this one. You don't want this. But this means what? Less than 1 means 0. Less than 1% means 0. This reminds me, there's a very interesting there's a phrase in Chinese, which I don't know whether anyone here studies Chinese, but anyway, there's a phrase in Chinese that says, if there's no one in the room, right? It's a funny expression. Not even half a person is there. In Chinese, it's said that way. It's kind of weird. I think it's kind of snarky actually. There's not even half a person there. You don't say there's no one there. There's not even half a person there. So it's 0 essentially, but it's a very strange way of thinking about it. So less than 1, 0. Okay, so like that. Okay, let's do another one. Okay, the probability of a newborn child getting a certain genetic disease is 0.25. Okay, the couple carry the disease. A couple carries the disease, and we have 4 children. What is the probability that 2 of them will get this one? This is actually, these kind of biological calculations are a thing, you know. There are certain genetic things that follow certain rules about probabilities applied to a lot of these kind of genetic calculations. So, do you understand the problem? So, if the couple has 4 children and X measures how many of the children end up having that genetic disease, then X will be binomial. What are the 2 parameters? 4 children, and the probability of success is 0.25. So all you need to do is, well, I would encourage you to get yourself familiarized with writing down the family it comes from. And when I say family, I'm not talking about this family, I'm saying the family of distributions. So it's the binomial 4 and 1, 4. So if X is the number of children who have or who inherit this disorder, I think it's 4C2. And you know the probability of getting it is independent from child to child, so 1/4 square. All right. Okay, this is a nice problem to talk about because it's going to look at, I think the binomial is quite basic, so I don't think I need you to even sit down and generate questions from it. I think it's pretty basic. I think most of you can get it. So let's just go on with this example. This is trying to incorporate binomial and something else. So a hospital receives 1/5 of its vaccine shipments from a certain company and the remainder from others. Okay. For company X, 10% of the things it ships out are ineffective, and for every other company, 2% are ineffective. So the hospital tests 30 and finds that one is ineffective. What is the probability this came from company X? I don't know whether you realize that this is kind of a tree question, but it's tree plus binomial. I'll tell you what. So first of all, the probability that any vial comes from company X is 1/5. We are told that. 1/5 of its supply is from company X. Do you agree, first of all, with these statements? Given that a vial comes from X, the probability that it is spoiled or ineffective is what we're told that. We are also told that if it's not from X, there's only a 2% rate of it being spoiled or ineffective. Now, you are testing 30, right? So W measures how many out of 30 are spoiled, but you notice it's binomial in any case, but it depends on where it got its source from. The numbers that are spoiled in a batch are, well, what I'm trying to say is this. The binomial process is correct because you are examining a sample of 30 from a potential pool that's like a sea of vaccine vials. That's why this can be modeled as a binomial. I'm not saying that you didn't just buy 30, you sampled 30 from a vast population of vaccine samples. That's why the binomial model applies, not because I've just been telling you, oh, this is finite. 30 is definitely finite, but the key assumption in a binomial is, of course, your sample is finite, but the assumption is that you got them from an infinite population. So number spoiled is binomial out of 30, but the probability of being spoiled depends on where the shipment came from. So look at what it is. You find that one vial was ineffective. Condition on the fact that you know that you saw one that was spoiled in the 30. See? Given that I know that I inspected 30 and one of them was out, what's the probability the source was X? Did you see that? So I'm incorporating the old Bayesian flipping argument. X given this is the given thing conditioned now on the thing coming from X times the probability of anything coming from X in the first place over probability of uh, of there being one spoiled at all. Okay. Now, what do I mean by probability spoiled? Okay, so this is not worded in the best possible way. Basically, what I mean is you have to divide. It's one spot in 30. I shortened it. Okay, it should be probability of one spot in 30. But one spot in 30 can come from an X source or a non-X source. There's nothing new here. This is exactly what we're talking about when it comes to the total probability of there being one spot in 30. You can have one spot in 30 whether you got it from X or whether you didn't. The only twist here is these probabilities are now obtained using the binomial. Everything else is the same. You learn Bayes' rule. You know the law of the total probability. Right? You know you can have one spot in 30 whether it came from X or it didn't. And the only thing that's new here is the fact that the probability of there being one spot in 30 when it is from X is this binomial, and it is this binomial if it came not from X. And then you scale each one by the probability that something even comes from X, that is 1/5, and the probability that it did not come from X, it's 1/5. So quite a few concepts here. I will let you digest it a little bit. So first of all, there's a Bayesian argument. The Bayesian argument allows you to switch the roles of the conditioning and the conditioned, right? You get turn it around. And then this one, you remember that something can be spoiled whether it's from X or not from X. And then the rest is just slowly putting in the numbers in the correct place. And we have established this, right? If the source is X, the probability that out of 30 you have one spot is this. It's the binomial thing that we've been talking about all day long. So while this problem is quite straightforward, I feel it is worthwhile mentioning because it's not immediately clear sometimes how to do this. So that's why I wanted to show you this example. See, it's a binomial, but it's conditioned on the fact that the binomial changes depending on what vial you're talking about, where or the source of the vials. All right. Okay. This is a nice problem which I want to discuss with you. This one's quite good. A company establishes a fund of 120. I know this looks pathetic, but it's scaled for your convenience. Okay? It's not just $120. A company establishes a fund and wants to pay an amount C to any of its 20 employees who achieve a high performance level during the coming year. Each employee has only a 2% chance of achieving a high performance level. Oh, that's terrible. Okay. Independent of any other employee. Determine the maximum value of C, and here's the twist, for which the probability is less than 1% that the fund will be inadequate to cover all payments for high performance. Do you even understand the question? Can you relate that, right? You have $120 to pay, okay? And you want to pay something, and your job is to find out what C can be to any employee that achieves high performance. Now, you are also told there's only a 2% chance that you will be considered high performance, okay? Now, determine what C can be so that there is less than 1% chance that you don't have enough money to cover. So in other words, saying this, what is the probability there? How many people can you give the award to? In other words, how small must you make, how large can the award be to make sure that you have enough to give it to all high performance employees that come out of that group? Okay, I want you to, in the remaining time, I want you to think about this in your group. So this is an ICT. So I want you to think about, it is a binomial question, it's mysteriously enough, because it involves 20 people, don't forget. There are 20 people to think about, okay? With an independent, all independent, and a fixed probability of achieving high performance, okay? So give it a try, see if you can, all right? maybe if you think about it this way, it might help you. What is the distribution of the number of high performance employees that could be? Yes, you could have all 20, but isn't that like super improbable? Yeah. So write down how many, what is the random variable that measures how many of the employees actually end up being high performance? Yes, potentially it could be all 20, potentially none. That's why this is a binomial question. See, and why do I need to tell you? Determine what C is so that there is less than 1% chance that you cannot cover the payments to all your worthy employees. Why is that 1% probability given? Don't confuse this 1% thing with the 2%. This is the binomial probability. The 1% is a requirement put there. That means there is a slight chance that the company will be embarrassed, basically. That's what we're trying to say. So to protect ourselves, to give us a 99% protection from embarrassment, basically. How much can I promise to give so that I'm at least 99% sure that I can cover the cost of rewarding all my high performance employees? Give that a think. Okay? You might have to do some trial and error, Then ask yourself, what is the probability of there being how many extra employees and all that? So you have to actually compute a few probabilities.
Should we just start like?
Yeah, start with zero.
Okay, so let's.
If you count once over to the guess, none. Don't bother with this. It's quite high. That's right. Okay. That's right.